Here, dear students, we're going to enter the Chapter 4, Introduction to Neural Learning, Gradient Descent. In this chapter, you will learn: do neural networks make accurate predictions? Why measure error? Hot and cold learning, calculating both direction and amount from error. Gradient descent, learning is just reducing error. Derivatives and how to use them to learn. Divergence and alpha. The only relevant test of the validity of a hypothesis is comparison of its predictions with experiments. The meaning of this sentence is the only way to test whether your assumption is right is to say if it's really happened in the real world. Predict, compare, and learn. In Chapter 3, you'll learn about the paradigm predict, compare, and learn, and we dive deep into the first step, predict. In the process, you'll learn a myriad of things, including the major parts of neural networks, nodes and weights, how datasets fit into networks, matching the number of data points coming in at once, and how to use a neural network to make a prediction. Perhaps this process begged the question: how do we set weight values so the network predicts accurately? Answering this question is the main focus of this chapter, as we cover the next two steps of the paradigm, compare and learn. Comparing gives a measurement of how much a prediction missed by. Once you made a prediction, the next step is to evaluate how well you did. This may seem like a simple concept, but you'll find that coming up with a good way to measure error is one of the most important and complicated subjects of deep learning. There are many properties of measuring error that you've likely been doing in your whole life without realizing it. Perhaps you, or someone you know, amplify bigger errors while ignoring very small ones. In this chapter, you'll learn how to mathematically teach a network to do this. You'll also learn the error is always positive. We will consider the analogy of an archer hitting a target. Whether the shot is too low by an inch or too high by an inch, the error is still just 1 inch. In the neural network compare step, you need to consider these kinds of properties when measuring error. As a heads up, in this chapter, we evaluate only one simple way of measuring error, mean squared error. It's but one of many ways to evaluate the accuracy of a neural network. This step will give you a sense for how much you missed, but that isn't enough to be able to learn. The output of the compare logic is a hot or cold type signal. Giving some prediction, you'll calculate an error measure that says either a lot or a little. It won't tell you why you missed, what direction you missed, or what you should do to fix the error in the next time. It more or less says big mess, little mess, or perfect prediction. What to do about the error is captured in the next step, learn. Learning tells each weight how it can change to reduce an error. Learning is all about error attribution, or the art of figuring out how each weight played its part in creating error. It's the blame game of deep learning. In this chapter, we'll spend many pages looking at the most popular version of the deep learning blame game, gradient descent. At the end of the day, it results in computing a number for each weight. That number represents how the weight should be higher or lower in order to reduce the error. Then you'll move the weight according to that number, and you'll be finished. Compare, does your network make good predictions? Let's measure in the arrow and find out. Execute the following code in your chapter notebook. It should be print out 0.3, the knob weight equal to 0.5, the input equal to 0.5, the goal prediction equal to 0.8, the prediction equal to input times the knob weight, the error equal to the prediction minus the goal prediction, and we have to calculate its squared value. Forces the row arrow to be positive by multiplying it by itself. Negative arrow wouldn't make sense. Okay. What is the goal prediction variable? Much like input, goal prediction is the number you recorded in the real world somewhere. But it's usually something hard to observe, like the percentage of people who did wear sweatshirts given the temperature, or whether the batter did hit a home run given his batting average. Why is the arrow squared? Think about an archer hitting a target. When the shot hits 2 inches too high, how much did the anchor miss by? When the shot hits 2 inches too low, how much did the anchor miss by? Both times the archer missed by only 2 inches. The primary reason to square how much you missed is that it forces the output to be positive. Prediction minus the goal prediction could be negative in some situations. Doesn't squaring make big arrows greater than 1 bigger and small arrows like smaller than 1 smaller? Yeah, it's kind of a weird way of measuring arrow, but it turns out that amplifying big arrows and reducing small arrows is okay. Later, you'll use this arrow to help the network learn, and you'd rather it pay attention to the big arrows and not worry so much about the small ones. Good parents are like this, too. They practically ignore arrows if they are small enough, breaking the lid on your pencil, but may go unclear for big arrows, like crashing a car. Yes, because we just doesn't care about the small arrows we made. It's not a big deal, but for the big arrow, we have to take care of it. Why measure arrow? Measuring arrow simplifies the problem. The goal of training a neural network is to make correct predictions. That's what you want, and in the most pragmatic word. As mentioned in the preceding chapter, you want the network to take input that you can easily calculate, like the today's stock price, and predict things that are hard to calculate, like the tomorrow's stock price. That's what makes a neural network useful. It turns out that changing knob weight to make the network correctly predict goal prediction is slightly more complicated than changing the knob weight to make error equal to 0. There's something more conscious about looking at the problem this way. Ultimately, both statements stay the same thing, but trying to get the error to 0 seems more straightforward. Different ways of measuring error prioritize error differently. If this is a bit of a stretch right now, that's okay. But think back to what I said earlier. By squaring the error, numbers that are less than 1, it will get smaller, whereas numbers that are greater than 1, it get bigger. You're going to change what I call pure error, so that big errors become very big and smaller errors quickly become nothing. By measuring error this way, you can prioritize big errors over smaller ones. When you have somewhat large pure arrows, say like 10, you tell yourself that you have very large arrow. 10 times 10 equal to 100. And in contrast, when you have small pure arrows like 0.01, you tell yourself that you have a very small arrow. Say, what I mean about prioritizing, it's just modifying what you consider to be arrow so that you amplify big ones and largely ignore small ones. In contrast, if you look the absolute value instead of squaring the arrow, you wouldn't have this type of prioritization. The arrow would just be positive version of the pure arrow, which would be fine but different. More on this later. So why do you want only positive arrow? Well, eventually you'll be working with millions of input to goal prediction pairs, and we will still want to make accurate predictions, so you'll try to take the average arrow down to 0. This presents a problem if the arrow can be positive and negative. Imagine if you were trying to get the neural network to correctly predict 2 data points, 2 input goal prediction pairs. If the first had an error of 1000 and the second had an error of negative 1000, then the average error would be 0. You would fool yourself into thinking that you predicted right when you missed by 1000 each time. That would be really bad. Thus, you want the error of each prediction to always be positive, and only in this way they don't accidentally cancel each other out when you average them. What's the simplest form of neural network? Learning using the Hertz or code method. At the end of the day, learning is really about one thing: adjusting norm weight either up or down so the error is reduced. If you keep doing this and the error goes to 0, you're done learning. How do you know whether to turn the norm up or down? Well, you try both up and down and say which one reduces the error. Okay, that's a genius idea for that. I didn't know that before. Whichever one reduces the error is used to update the norm weight. It's simple but effective. After you do this over and over again, eventually the error would be equal to 0, which means the neural network is predicting with perfect accuracy. Hard and cold learning. Hard and cold learning means waggling the weights to say which direction reduces the error the most, moving the weights in that direction and repeating until the error gets to 0. Say like we have a simplest empty network. We got the input, the weight, and the output. The weight equal to 0.1. The learning rate equal to 0.01. We define a neural network. We define a function. This function takes input and weight, and we time the input with the weight. We get the prediction. Predict, making a prediction and evaluating error. So it's like we got the number of times 8.5. We got win or not binary. If it's 1, it means win. The input equal to number of elements, the first element of that last. And we also have the first element of win or not binary. We feed the input and weight to the neural network, and we get the output, prediction. We calculate the error by using this statement, prediction minus the real value, the true value. Then we calculate its squared value. In this way, we get the error. The error is a way to measure how much you missed. There are multiple ways to calculate error, as you'll learn later. This one is mean squared error. Compare making a prediction with a higher weight and evaluating error. We want to move the weight so the error goes downward. Let's try moving the weight up and down using weight plus the learning rate or weight minus the learning rate to say which one has the lowest error. Again, the learning rate equal to 0.1. The prediction up equal to neural network. We gave it this function two parameters, the input and the weight plus the learning rate. So in this way, we will get the result if we up the weight by the learning rate. Also, we could make a prediction with a lower weight and evaluating the errors. In this way, we will get another error. So in this time, we have to compare the errors and set in the new weight. If the error greater than, no, it's not like that. If the error up greater than the error down, that means we have to let the weight up. Or if the error down smaller than error up, we should let the weight down a little bit. So it's all about finding the best direction up or down to let the weight smaller, to let the error smaller. These last 5 steps are one iteration of hard and cold learning. Fortunately, this iteration got us pretty close to the correct answer all by itself. The new error is only 0.004, but under normal circumstances, we would have to repeat this process many times to find the correct weights. Some people have to train their networks for weeks or months before they find a good enough weight configuration. This reveals what learning in neural networks really is: a search problem. You are searching for the best possible configuration of weights, so the network's error falls to 0 and predicts perfectly. As with all the other forms of search, you might not find exactly what you are looking for, and even if you do, it may take some time. Next, we will use hot and cold learning for slightly more difficult predictions so you can see this searching in action. Hot and cold learning. This is perhaps the simplest form of learning. Execute the following code in your chapter notebook. New neural network modifications are in bold. This code attempts to correct the prediction 0.8. So now students just pause the video and try to type those code by yourself. Okay, I almost finished the coding here. I'm going to run this code. When I run this code, what I say is something like this. The error just didn't go small. Yeah, it always keeps the same. Maybe I did something wrong at the process. Let's check it out. First, we define the weight and the input and the goal prediction. The step amount equal to that, and we do some range. We say the prediction equal to the input times the weight. The error equal to prediction minus the goal prediction squared. Oh, now I know where I did wrong here. I should use the down prediction. We calculate the up prediction and down prediction and do some compare. We will say if the down arrow less than the up arrow, we will use the down arrow. We will do a down action. If the down arrow greater than up arrow, we will do a up action. Now let's say the results. As you can see, the arrow just falls to the 0 gradually. and the last prediction is something close to 0.8. Cool. Characteristics of hot and cold learning. It's simple. Hot and cold learning is simple. After making a prediction, you predict 2 more times, once with a slightly higher weight, and again with a slightly lower weight. You then move the weight, depending on which direction, give a smaller error. Repeating this enough times, eventually you'll get an error that's close to 0. Why did I iterate exactly 1,100 and plus 1 times? The neural network in the example reaches 0.8 after exactly that many iterations. If you go past that, it waggles back and forth between 0.8 and just above or below 0.8, making for a less pretty error log printed at the bottom of the left page. Feel free to try it. Okay, I know that. It will keep doing that, but it will never reach the 0.8. The problem 1 is inefficient. You have to predict multiple times to make a single non-weight update. This seems very inefficient. Problem 2. Sometimes it's impossible to predict the exact goal prediction with a set step amount unless the perfect weight is exactly n times step amount away. The network will eventually overshot by some number less than the step amount. When it does, it will then start alternating back and forth between each side of the goal prediction or between the target value. Set step amount to 0.2 to see this in action. If you set the step amount to 10, you'll really break it. When I try this, I see the following output. It never remotely comes close to 0.8. The real problem is that even though you know the correct direction to move weight, you don't know the correct amount. You don't know the correct value, how much value you should add or subscribe. Instead, you pick a fixed one at random step amount. Furthermore, this amount has nothing to do with error. Whether error is big or tiny, step amount is the same. So, hot and cold learning is kind of a bummer. It's inefficient because you predict 3 times for each weight update, and the step amount is arbitrary, which can prevent you from learning the correct weight value. What if you had a way to compute both direction and amount for each weight without having to repeatedly make predictions? Calculating both direction and amount from error. Let's measure the error and find the direction and amount. Execute the code in your Jupyter notebook. I already did that at my Jupyter notebook. Here it is. The weight equal to 0.5, the goal prediction equal to 0.8, the input equal to 0.5. For iteration in range 20, the prediction equal to input times the weight, or dot the weight. Error equal to the prediction minus the goal prediction squared. Direction and amount equal to the prediction minus the goal prediction times the input. The weight equal to the weight minus the direction and amount. And if we execute this code, you'll see the prediction will eventually go to some value that near the 0.8. Here it is. By using this code, you don't have to calculate it twice. You don't have to calculate the up or down prediction errors. What you see here is a superior form of learning known as gradient descent. This method allows you to in a single line of code shown here like this. Calculate both the direction and the amount of you should change the weight to reduce the error. So it only requires one line of code. That's genius. I don't know who did this, but they must be genius. The direction is represented by the sign of that value. It can either positive or negative, and the positive or negative stuff defines the direction, and the volume defines the amount, and it is related to the input and the error. If the error gets smaller, the amount gets smaller. If the error gets bigger, the changing amount will be bigger. So it's actually a relative process. It's a relative value. It depends on the error and the input. What is direction and amount? Direction and amount represents how you want to change weight. The first part is what I call pure error, which equals prediction minus the goal prediction, or the value, or the predicted value minus the real value. More about this shortly. The second part is the multiplication by the input that performs scaling, negative reversal, and stopping, modifying the pure error so it's ready to update the weight. What is the pure error? The pure error is prediction minus the goal prediction, which indicates the raw direction and amount you missed. If this is a positive number, you predicted too high, and vice versa. If this is a big number, you missed by a big amount, and so on. What are scaling, negative reversal, and stopping? These three attributes have the combined effect of translating the pure error into the absolute amount you want to change weight. They do so by addressing three major edge cases where the pure error isn't sufficient to make a good modification to weight. To be honest, I don't understand this line of stuff. I don't know what is it he was talking about at this paragraph. But I indeed know that if the error equal to 0, 0 times anything would be still equal to 0, so it will stop updating the weight. What is stopping? Stopping is the first and the simplest effect on the pure error caused by multiplying it by input. Imagine plugging a CD player into your stereo. If you turned the volume all the way up, but the CD player was off, the volume change wouldn't matter. Stopping addresses this in a neural network. If input is 0, then it will force direction and amount to also by 0. You don't change the value when the input is 0. Okay, it's something that I just said before. What is negative reversal? This is probably the most difficult and important effect. Normally, when input is positive, moving weight upward makes the prediction move upward. But if the input is negative, then all of a sudden weight changes directions. When input is negative, moving weight up makes the prediction go down. It's reversed. How do you address this? Well, multiplying the pure error by input will reverse the sign of direction and amount in the event that input is negative. This is negative reverse, ensuring that the weight moves in the correct direction, even if the input is negative. What is scaling? Scaling is the third effect on the pure error caused by multiplying it by input. Logically, if the input is big, your weight update should also be big. This is more of a sad effect because it often goes out of control. Later, you'll use alpha to address when that happens. When you run the previous code, you should see the following output. The last steps correctly approach 0.8. In this example, you saw gradient descent in action in a bit of an oversimplified environment. Next, you'll see it in a more native environment. Some terminology will be different, but I'll code it in a way that makes it more obvious applicable to other kinds of networks, such as those with multiple inputs and outputs. One iteration of gradient descent. This performs a weight update on a single training example. Input to true pair. An empty network. The input data, the protected data. The weight equal to 0.1. The alpha equal to 0.01. So we don't have to define the learning rate anymore. We define the narrow network, the input and the weight. Prediction equal to that. Making a prediction and evaluating error. Yes, it's still the same as we have seen before. Calculating the node delta and putting it on the output node. Delta equal to prediction minus the goal prediction, but it's something like the error, I guess. Why he just did that again? Data is a measurement of how much this node missed. The true prediction is 1.0, and the network's prediction was 0.85, so the network was too low by 0.15. Thus, delta is negative 0.15. The primary difference between gradient descent and this implementation is the new variable delta. It's a raw amount that the node was too high or too low. Instead of computing direction and amount directly, you first calculate how much you want the output node to be different. Only then do you compute direction and amount to change weight. Okay, then we just add another line of code. Weight delta equal to input times delta. It's like the same stuff, but with two lines of code. The weight data is a measure of how much a weight cost the network to miss. You calculate it by multiplying the weight's output node, delta, by the weight's input. Thus, you create each weight data by scaling its output node delta by the weight's input. This amounts for the three aforementioned properties of direction and amount, scaling, negative reverse, and stopping. Fixed before training, the alpha equal to 0.01. The weight now equal to something like this. The weight data times alpha. You multiply weight delta by a small number, alpha, before using it to update the weight. This lets you control how fast the network learns. If it learns too fast, it can update weights too aggressively and overshoot. Note that the weight update made the same change, small increase, as hot and cold learning. Whoa, I don't know why he want to introduce us the new method. I have no idea right now. Learning is just reducing the error. You can modify weight to reduce the error. Putting together the code from the previous pages, we now have the following. The weight, the goal prediction, the input. For iteration in range, prediction equal to input times the weight, the error equal to the prediction minus the goal prediction squared. The delta equal to the delta equal to prediction minus goal prediction. Weight delta equal to delta times the input. The weight equal to the weight minus the weight delta. Yeah, in this way we still can have the error value and also change the weight. The golden method for learning. The approach adjusts each weight in the correct direction and by the correct amount so that error reduces to 0. All you are trying to do is figure out the right direction and amount to modify weight so that error goes down. The secret lies in the provide and error calculations. Notice that you use prediction inside the error calculation. Let's replace the prediction variable with the code used to generate it. Alright, it's the same thing but with one line of code. Error equal to input times weight minus the goal prediction. Yeah, this is the current prediction input times weight, and this is a goal prediction. We do a subtraction so we can get the error, and we're gonna square it to get the real error or the mean squared error. This doesn't change the value of error at all. It just combines the two lines of code and computes error directly. Remember that input and goal prediction are fixed at 0.5 and 0.8 respectively. You set them before the network starts training. So if you replace the variables' names with the values, the secret becomes clear. The secret: for any input and goal prediction, an exact relationship is defined between error and weight, found by combining the prediction and error formulas in this case. Let's say you just increased the weight by 0.5. If there's an exact relationship between the error and the weight, you should be able to calculate how much this also moves the error. What if you wanted to move error in a specific direction? Could it be done? Here's a graph about the error and the weight. This graph represents every value of error for every weight according to the relationship in the previous formula. Notice it makes a nice ball shape. The black dot is at the points of both the correct weight and error. The dotted circle is where you want to be, the error equal to 0. The slope points to the bottom of the bow, slowest error. No matter where you are in the bow, you can use this slope to help the neural network reduce the error. I was a little bit confused here. I don't know what he was talking about actually. I don't know the meaning of this graph, but we will figure out, I hope. Let's watch several steps of the learning. Will we eventually find the bottom of the bow, the weight, the goal prediction, the input? For iteration in range, we print out the weight. Prediction equal to input times weight. Error equal to prediction minus the goal prediction squared. The data equal to prediction minus goal prediction. The weight data equal to data times the input. The weight equal to weight minus the weight delta. We print out the error, the prediction, and the data, and the weight. A big weight increase. The weight data equal to negative 0.88. Row error modifies for scaling, negative reversal, and stopping per this weight and input. Okay, I still don't know what he was talking about here. Overshot a bit, let's go back the other way. So in this graph it's negative, but in this graph it's a positive weight, I guess. Overshot again, let's go back, but only a little. Okay, we are pretty much there. So it's like the delta, the delta. How to understand the delta? Okay, the delta is a math item. It's a mathematical item. You say the delta, it means the difference between two values. And the data at the first it's a very big value, but with the time goes by, you can see the data goes down little by little, and eventually it goes to 0. When the data goes to 0, the error also goes to 0. I mean, the data controls the amount of changing. The amount of changing. When the data is bigger, the change the training made is also big. Why does this work? What is weight data?
Delta.
Let's back up and talk about functions. What is a function? How do you understand one? Consider this function. Define a function. It returns x times 2. A function takes some numbers as input and gives you another number as output. As you can imagine, this means the function defines some sort of relationship between the input numbers and the output numbers. Perhaps you can also see why the ability to learn a function is so powerful. It lets you take some numbers, say image pixels, and convert them into another numbers. Say the probability that the image contains a cut. Every function has what you might call moving parts, pieces you can tweak or change to make the output the function generates different. Consider my function in the previous example. Ask yourself, what is controlling the relationship between the input and output of that function? The answer is the 2. Ask the same question about the following function. This is also a function, though it may seem like a line of code to you. What's controlling the relationship between the input and the output arrow? Plenty of things are. This function is a bit more complicated. The goal prediction, the input, the tool, the weight, and all the parentheses and algebra rag operations, addition, subtraction, and so on, play a part in calculating the error. Tricking in any one of them would change the error. This is important to consider. As a thought exercise, consider changing the goal prediction to reduce the error. So how can you reduce the error by changing the goal prediction? For me, I would say I would make this value as close to the input times weight as possible, because if they do, the whole sense from this to this will equal to 0, and 0 is the smallest error we could ever get. This is silly but totally double. In life, you might call this setting goals to be whatever your capability is giving up. You are the line that you missed that wouldn't do. Okay, what he was trying to say, I don't understand. What if you changed the input until your error went to 0? Well, that's akin to seeing the word as you want to say it instead of as it actually is. You're changing the input data until you are predicting what you want to predict. This is loosely how inception lesson works. Now consider changing the tool, or the additions, subtractions, or multiplications. This is just changing how you calculate error in the first place. The error calculation is meaningless if it doesn't actually give a good measure of how much you missed. What's left? The only variable remaining is weight. Adjusting it doesn't change your perception of the world, doesn't change your goal, and doesn't destroy your error measure. Changing weight means the function conforms the patterns in the data. By forcing the rest of the function to be unchanging, you force the function to correctly model some pattern in the data. This is only allowed to modify how the network predicts. To sum up, you modify specific parts of an error function. until the error value goes to 0. This error function is calculated using a combination of variables, some of which you can change, for example the weights, and some of which you can't, for example the input data, the output data, and the error logic. So now I have a little bit of code about what he was trying to say. What he was trying to say is you cannot change the input data because that's the real world data. And you cannot change the output data because that's something you wanted. You cannot control that. You want the machine to tell you the output data. And the error logic, you also cannot change that because it's the mathematical thing. It's the algorithm. The algorithm is fixed. You cannot change it. The only thing you can change is the weight because weight, it's nothing but variables, a fixed variable. Once it fixed to a perfect value, you probably won't you will use it. But when the times change, when the situation changes, you have to change the weights according to the situation. So the weights is the only thing that you need to change. You can change it. Key takeaway: you can modify anything in the prediction calculation except the input. We'll spend the rest of the book, and many deep learning researchers will spend the rest of their lives trying everything you can imagine on that prediction calculation so that it can make good predictions. Learning is all about automatically changing the prediction function so that it makes good prediction, so that the subsequent error goes down to. Now that you know what you are allowed to change, how do you go about doing the changing? That's the good stuff, and that's the machine learning, right? In the next section, we are going to talk about exactly that. Internal version on one concept. Learning is just adjusting the weight to reduce the error to 0. So far in this chapter, we've been hammering on the idea that learning is really just about adjusting weight to reduce the error to 0. This is a sacred source. Truth be told, knowing how to do this is all about understanding the relationship between the weight and the error. If you understand this relationship, you can know how to adjust weight to reduce the error. What do I mean by understand the relationship? Well, to understand the relationship between two variables is to understand how changing one variable changes the other. In this case, what you are really after is the sensitivity between those two variables. Sensitivity is another name for direction and amount. You want to know how sensitivity error is to weight. You want to know the direction and the amount that error changes when you change the weight. This is a goal. So far, you've seen two different methods that attempt to help you understand this relationship. When you were wrestling with hard and cold learning and studying its effect on the error, you were experimentally studying the relationship between those two variables. It's like walking into a room with 15 different unlabeled light switches. You start flipping them on and off to learn about the relationship to various lights in the room. You did the same thing to study the relationship between weight and error. You waggled the weight up and down and watched for how it changed the error. Once you knew the relationship, you could move the weight in the right direction using two simple if statements. If the down arrow less than the up arrow, we will do the down action. If the down arrow greater than the up arrow, we will do the up action. Now let's go back to the earlier formula that combined the prediction and error logic. As mentioned, they correctly define an exact relationship between the error and weight. It's something like this. The error equal to the input times the weight minus the goal prediction squared. This line of code, ladies and gentlemen, is the secret. This is a formula. This is a relationship between error and weight. This relationship is exact, it's computable, it's universal, and will always be. Okay, now you can use this formula to know how to change weight so that error moves in a popular direction. That is the right question. Stop. I beg you, stop and appreciate this moment. This formula is the exact relationship between these two variables, and now you are going to figure out how to change one variable to move the other variable in a particular direction. As it turns out, there's a method for doing this for any formula you use it to reduce error. A box with rods poking out of it. Picture yourself sitting in front of a cardboard box that has two circular rods sticking through two lead holes. The blue rod is sticking out of the box by 2 inches, and the red rod is sticking out of the box by 4 inches. Imagine that I tell you these rods were connected, but I won't tell you in what way. You have to experiment to figure it out. So you take the blue rod and push it in 1 inch, and watch us while you are pushing. The red rod also moves into the box by 2 inches. Then you pull the blue rod back out 1 inch, and the red rod follows again, pulling out by 2 inches. What did you learn? Well, there seems to be a relationship between the red and blue rods. However much you move the blue rod, the red rod will move by twice as much. You might say the following is true. The red lines equal to the blue lines times 2. As it turns out, there's a formula definition for when I tug on this part, how much does this other part move? It's called a derivative, and all it really means is how much does rod X move when I tug on rod Y. In the case of the red and blue rods, the derivative for how much does the red move when I tug on blue is 2, just 2. Why it is 2? That's multiplicative relationship determined by the formula. Notice that you always have the derivative between two variables. You are always looking to know how one variable moves when you change another one. If the derivative is positive, then when you change one variable, the other will move in the same direction. As if the derivative is negative, then when you change the one variable, the other will move in the opposite direction. Yeah, it's a mathematical conception. Consider a few examples. Because the derivative of red length compared to the length is 2, both numbers move in the same direction. More specifically, red will move twice as much as blue in the same direction. If the derivative had been -1, the red would move in the opposite direction by the same amount. Thus, given a function, the derivative represents the direction and the amount of one variable changes if you change the other variable. This is exactly what we were looking for. Derivatives. Take 2. Still a little unsure about them. Let's take another perspective. Yeah, I don't know what he was talking about in the last example. I cannot imagine that, but I can understand the mathematical conception under that. I've heard people explain derivatives 2 ways. One way is all about understanding how one variable in a function changes when you move another variable. The other way says that a derivative is the slope at a point on a line or curve. As it turns out, if you take a function and plot it or drop it, the slope of the line you plot is the same thing as how much one variable changes when you change the other. Let me show you by plotting our favorite function. This is the general function for machine learning error calculation. Remember, the goal prediction and input are fixed, so you can rewrite this function like this. Yeah, it's a constant number. It is fixed. Because there are only two variables left that change, all of the rest of them are fixed. You can take every weight and compute the error that goes with it. Let's plot them or drop them. As you can see, the plot looks like a big U-shaped curve. Here it is a big U shape of graph. Notice that there's also a point in the middle where arrow equal to 0. When the point goes to here, the slope will probably equal to 0. Also, notice that to the right of the point, the shape of the line is positive to the right of that point. So, in the right side of this graph, the shape is positive. And to the left of that point, or the left graph, the slope of the line is negative. Here you can see the left side of this graph, the slope of that line is negative, if you know basic high school math. Perhaps even more interesting, the further away from the goal weight you move, the steeper the slope gets. Yes, of course. The more far away from the center point of this weight, you'll get a more steeper slope. These are useful properties. The slope's sign gives you the direction, and the slope's steepness gives you the amount. You can use both of these to help find the goal weight. It is at the center of this. Even now, when I look at that curve, it's easy for me to lose track of what represents. It's similar to the hot and cold method for learning. If you tried every possible value for weight and plotted it out, you would get this curve. And what's remarkable about derivatives is that they can say past the big formula for computing. At the beginning of this section and see this curve, you can compute the slope or derivative of that line for any value of the weight. You can then use this slope derivative to figure out which direction reduces the error. Even better, based on the steepness, you can get at least some idea of how far away you are from the optimal point where the slope is 0, although not an exact answer, as you'll learn more about that later. What you really need to know: with derivatives, you can pick any two variables in any function and know how they interact. Take a look at this big wrapper of a formula. Y equal to beta times 2 plus epsilon plus 22 minus x times 1 over 2. Here's what you need to know about derivatives. For any function, this one, you can pick any two variables and understand the relationship with each other. For any function, you can pick two variables and plot them on an xy graph, as we did earlier. For any function, you can pick two variables and compute how much one changes when you change the other. Thus, for any function, you can learn how to change one variable so that you can move another variable in a direction. Sorry to harp on this point, but it's important that you know this in your bones. Bottom line, in this book, you are going to build neural networks. A neural network is really just one thing, a bunch of weights you use to compute an arrow function. And for any arrow function, no matter how complicated, you can compute the relationship between any weight and the final arrow of the network. With this information, you can change each weight in the neural network to reduce the error down to 0, and that's exactly what you are going to do. Okay, let's just read it again. I was a little bit confused here. In this book, you are going to build neural networks. A neural network is really just one thing, a bunch of weights you use to compute an arrow. We use the weights to compute the arrow function. I thought we will use the weights to compute the prediction. But here it gives us a different view of point. He said we use the weights to compute an arrow function. It's a fresh new idea. And for any arrow function, no matter how complicated it is, you can compute the relationship between any weight and the final arrow of the network. With this information, you can change each weight in the neural network to reduce the error down to 0. What you don't really need to know? Calculus. So it turns out the learning all the methods for taking any two variables in any function and computing the relationship takes about 3 semesters of the course. Truth be told, if you went through all 3 semesters so that you could learn how to do deep, you would use only a very small subset of what you learned. And really, calculus is just about memorizing and practicing every possible derivative rule for every possible function. Yes, of course, I agree with that. You don't have to learn the details about the derivative calculation because you can do it with a computer. The computer, for example, the Python library will help you to do that, so you don't have to learn it that well. In this book, I'm going to do what I typically do in real life, because I'm lazy, efficient. Look up the derivative in a reference table. All you need to know is what the derivative represents. It's a relationship between two variables in a function, so you can know how much one changes when you change the other. It's just the sensitivity between two variables. Yeah, I know that was a lot of information to say. It's the sensitivity between two variables, but it is. Note that this can include positive sensitivity when variables move together, negative sensitivity when they move in opposite directions, and zero sensitivity when one stays fixed regardless of what you do to the other. For example, y equal to 0 times x. Move x, the y won't change. Well, it will always equal to 0. Enough about derivatives. Let's get back to gradient descent. So, how to use a derivative to learn? Weight delta as your derivative. What's the difference between error and the derivative of error and weight? Error is a measure of how much you make. The derivative defines the relationship between each weight and how much you make. In other words, it tells you how much changing a weight contributes error. So now that you know this, how do you use it to move the arrow in a particular direction? You have learned the relationship between two variables in a function, but how do you exploit that relationship? As it turns out, this is incredibly visual and intuitive. Check out the arrow curve again. The black dot is where the weight starts out 0.5. The dotted circle is where you want to go there, the goal weight. Do you say the dotted line attracted? Do you say the dotted line attached to the black dot? That's the otherwise known as the derivative. It tells you at that point in the curve how much arrow changes when you change the weight. Notice that pointed downward is a negative slope. Yeah, here you can say the weight data in here is a negative number. Here, the slope of a line or curve always points in the opposite direction of the slowest point of the line or curve. So if you have a negative slope, you increase the weight to find the minimum of error. Check it out. So how do you use the derivative to find the error minimum, the lowest point in that error graph? You move the opposite direction of the slope, the opposite direction of the derivative. You can take each weight value, calculate its derivative with respect to error, and then change the weight in the opposite direction of that slope. That will move you to the minimum value or the target value. Remember, back to the goal again, you are trying to figure out the direction and amount to change the weight so the error goes down. A derivative gives you the relationship between any two variables in a function. You use the derivative to determine the relationship between any weight and error. You then move the weight in the opposite direction of the derivative to find the slowest weight. In this way, the neural network learns. This method for learning, finding error minimums, is called gradient descent. This line should seem intuitive. You move the weight value opposite the gradient value, which reduces error to zero. By opposite, I mean you increase the weight when you have a negative gradient, and worse, gravity. Does this graph look familiar for you? It's the same it's the same code that we saw before. The derivative here, it controls how fast the error changes, given changes in that weight. A big weight increase, the weight data equal to negative 0.8. It's negative, so it's quite big. And if that's delta or derivative is positive, then it means we are overshot. So we need to go back. Breaking gradient descent, just give me the code. The weight equal to 0.5, the goal prediction equal to 0.8, the input equal to 0.5 for iteration in range 20. The prediction equal to input times the weight, the error equal to the prediction minus the goal prediction squared. The delta equal to prediction minus the goal prediction. The weight delta equal to the input times the weight equal to weight minus the weight data. If you run this code, you'll see the result like this, or the output like this. Now that it works, let's play around with the starting weight, goal prediction, and numbers. You can set them all to just about anything, and the neural network will figure out how to predict the output given the input using the weights. See if you can find some combination the neural network can predict. I found that trying to break something is a great way to learn about it. Let's start by setting the input equal to 2, but still try to get the algorithm to predict 0.8. What you'll get is something like this. Well, that's not what you want. The prediction exploded. The alternate from negative to positive and negative to positive, getting farther away from the true answer at every step. In other words, every update to the weight overcorrects. In the next section, you'll learn more about how to combat this phenomenon. Why? Just because they just changed the input from 0.5 to 2. Visualizing the overcorrections. This is how it happens if you change the input value from 0.5 to 2. Overshot a bit. Let's go back. The other, you can see the black point go from the right to the left. Then it overshoots again. So you go back a little bit, but get a higher value somehow. Divergence. Sometimes neural networks explode in value. What really happened? The explosion in the error was caused by the fact that you made the input not consider how you are updating the weight. You have used the variable input. If the input is sufficiently large, this can make the weight update large even when the error is small. What happens when you have a large weight update and a small error? The network overcorrects. Yeah, of course, because you got a very, very big error. If the new error is even bigger, the network overcorrects even. This causes the phenomenon you saw earlier, called divergence. If you have a big input, the prediction is very sensitive to change in the weight because the prediction output equal to the input times the weight. This can cause the network to overcorrect. In other words, even though the weight is still starting at 0.5, the derivative at that point is very steep. See how tight the U-shaped arrow curve is in that graph. This is really intuitive. How do you predict? By multiplying the input by the weight. So if the input is huge, small changes in the weight will cause changes in the prediction. The error is very sensitive to the weight. In other words, the derivative is really big. How do you make it smaller? Introducing alpha. It's the simplest way to prevent overcorrecting weight updates. What's the problem you are trying to solve? That if the input is too big, then the weight update can overcorrect. What's the symptom? That when you overcorrect, the new derivative is even larger in magnitude than when you started. Stop and consider this for a second. Look again at the graph in the previous section to understand the system. Step 2 is even farther away from the goal, which means the derivative is even larger in magnitude. This causes step 3 to be even farther from the goal than step 2, and the neural network continues like that, demonstrating divergence. The symptom this overshoot. The solution is multiply the weight updates by a fraction to make it small. In most cases, this involves multiplying the weight update by a single real-valued number between 0 and 1, known as alpha. Note, this has no effect on the core issue, which is that the input is larger. It will also reduce the weight updates for inputs that aren't too large. Finding the appropriate alpha, even for state-of-the-art neural networks, is often done by guessing. Okay. You watch the error over time. If it's going up, then the alpha is too high, and you decrease it. If learning is happening too slowly, then the alpha is too low, and you increase it. There are other methods than simple gradient descent that attempt to account for this. Gradient descent is still very popular. Alpha in code. Where does our alpha parameter come into play? You just know that the alpha reduces the weight up so it doesn't overshoot. How does this affect the code? Well, you were updating the weights according to the following the weight equal to the weight minus the derivative. Accounting for alpha is a rather small change. As shown next, notice that if alpha is small, say 0.01, it will reduce the weight update considerably, thus preventing it from overshooting. That was easy. It's just something like this. We just have to use the alpha times the derivative. That was easy. Let's install alpha into the tiny implementation from the beginning of this chapter, and run it where input equal to 2, which previously didn't work. What happens when you make alpha crazy small or big? What about making it negative? I don't know. To be honest, I haven't used the alpha variable before when I read this book. When I using those popular framework like TensorFlow or Keras, I didn't use the alpha parameter. It's weird. Well, the tiniest neural network can now make good predictions again. How did I know to set the alpha to 0.1? To be honest, I tried it, and it worked. And despite all of the crazy advancements of deep learning in the past few years, most people just try several orders of magnitude or of alpha, 10, 1, 0.1, 0.01, and so on, and then trick it from there to say what works best. It's more art than science. There are more advanced ways to get to later, but for now, try various alphas until you get one that seems to work pretty well. Play with it. Memorizing. It's time to really learn this stuff. This may sound a bit intense, but I can't stress enough the value I have found from this exercise. Say if you can build the code from the previous section in a Jupyter notebook or PY file if you want from memory. I know that might seem like overkill, but I personally didn't have my click moment with neural networks until I was able to perform this task. Why does this work? Well, for starters, the only way to know you have gleaned all the information necessary from this chapter is to try to produce it from neural networks have lots of small moving parts, and it's easy to miss one. Why is this important for the rest of the book? In the following chapters, I'll be referring to the concepts discussed in this chapter as a faster piece, so that I can spend plenty of time on the newer material. It's very important that when I say something like aid your alpha parameterization to the weight update, you immediately recognize which concepts from this chapter I'm referring to. All that is to say, memorizing small bits of neural network code has been hugely beneficial for me personally, as well as for many individuals who have taken my advice on this subject in the past. Okay, the next section is chapter 5. We won't discuss it in this video. I would suggest you to do the same thing as the other told you to do, because it's very important to remember those core concepts or codes you had to use often. For me, for my personal experience, I think when you programming, the memory stuff will take you almost a lot of time thinking in mathematics. than thinking mathematics. Okay, I'll pause this video and do this exercise by myself. Okay, this is what I did when I try to, rewrite the whole thing based on my memory. And I hope this will work. Let's run it. And we got something like this. The arrow just getting smaller and smaller from the 0.5 go to 0.0, then somehow get higher again. I don't know why that's happening for. So I should change the range to a large value and say what will happen. Okay, it seems like the error just getting strange. Maybe I should do something like this, get the integer of that arrow. Okay, this time the arrow just it's just theirs, and the prediction was right in the. Oh, this number maybe means something that's very, very small. What will happen if we change the input to 2, like the other tried? Oh, as you can see, the arrow just gets very, very big. It's not a good idea. It's overshooting and diverging. We should find a way to solve this problem. The other said we should add another parameter, the alpha. I don't know how to spell it, so I have to check it out. The alpha, ALPHA. ALPHA, the alpha. Let's say it is equal to 0.1, and we have to add this alpha to a calculation where I should add it to. Okay, it's right in here. When we change the weight, we have to do some calculation or do some changes about the data. We want to get a smaller data, so we should say data times alpha. Okay, now let's try to run this again. Now you say that we still get a right prediction and the right error that near the arrow was getting, and it's generally close to the 0. Okay, that's it. I hope you will like this video as I did, and also I love this author because he just taught us the basic stuff that under those framework, those basics of machine learning. And that's it. I will see you in the next video. Bye.